Wel- Welcome to this new video where we'll see the edit distance problem. So what does the problem say? It says, given two words as strings word1 and word2, create a function that returns the minimum number of operations required to convert word1 to word2. Note that we have three possible operations. We can either insert a character, or remove a character, or replace a character. I hope that you try to solve the problem, so let's start. Let's suppose that we have the word inside and we want to convert it to index. For the first letter, there is no problem because it's the same letter. We have no operation to do, we just move both pointers. Same thing here, they have the same second letter, so we just continue. But here the letter is different, so to fix it we have to perform an operation. But which one? Because we have three possibilities. We can either remove the character and move on word 1, or insert the character and move on word 2, or replace the character on word 1 with the one on word 2 and move in both of them. And because we don't know what operation will lead to the minimum number of operations required, we have to try them all. In other words, we call the same function when we consider that we removed, so with i+1, and when we consider that we inserted, so with g+1, and when we consider that we replaced, so with i+1 and g+1. And after getting the result of those function calls, we take the minimum among them, because we are searching for the minimum operations required, and we add 1 to it to count the operation we did now. And this process gets repeated on each function call until arriving at the base case. You know how recursion stuff works. Here I didn't draw the whole recursion tree because it's way too big. But here is the final result, we get 3 at the end. And it's the right result because to go from word 1, which is inside, to word 2, which is index, we can remove the s, remove the I, and insert the x at the end, and we get index with only 3 operations. Before moving to the code, we have to talk about base cases of this recursive solution. We have 2 base cases. We have the case where we reach the end of word 1, when I becomes equal to the length of word 1. In that case, we have to insert all remaining characters of word 2 starting from the pointer g, which means that we have to return the length of word 2 minus g. The second base case, the opposite, when we reach the end of word 2, when g becomes equal to the length of word 2. In that case, we have to remove all remaining characters of word 1, which means that we have to do length of word 1 minus I operations, so we return length of word 1 minus I. Now we can check the code. We first define the function, then we have base cases. If I is equal to length of word 1, then we return length of word 2 minus g, else if g is equal to length of word 2, then we return length of word 1 minus I. Now, in the general case, it depends if the characters at index I and g are equal, because in that case, we have no operation to do, we just move in both word 1 and word 2. So if word 1 of I is equal to word 2 of g, we return the function called with i+1 and g+1. Else, we have the case where characters don't match. We said that we have to call the function thrice, and we take the minimum and we add 1 to it. So we return 1 plus the minimum between the function called with i+1 when we remove, and the function called with g+1 when we insert, and the function called with i+1 and g+1 when we replace, and we got our function. And by the way, the value that we calculated now is called the Levenshtein distance. You can find a Wikipedia article about it. They defined it using this formula. But it's basically what we did here, it's just that they started from the end of both words and they stopped when either I or g becomes 0. For the time complexity of this solution, you can see that in the general case, we are calling the same function thrice, and the recursion has m plus m levels, so we get a time complexity of 3 power m plus m. And for the space complexity, as said earlier, the recursion tree has n plus m levels, so the maximum call stack size is m plus m. We get a space complexity of O of m plus m. But it's obvious that we won't stop here because our recursion tree has repeated function calls, so we will use either memoization or tabulation to reduce time complexity. And here we will use tabulation because we need all intermediate values, so we can't just use a matrix of n plus 1 rows and n plus 1 columns. Okay, but how to fill this matrix? Know that each cell dp of ig represents the number of operations required to transform word 1 until index I to word 2 until index g. For example, for the first row, to transform the empty string to the empty string, we need 0 operations. Then to transform the empty string to the string I, we need 1 operation. Then to transform the empty string to the string in, we need 2 operations, and so on until the end. For the first column, to transform the empty string to the empty string, we need 0 operations. Then to transform the string I to the empty string, we need 1 removal, 1 operation. Then to transform the string into the empty string, we need 2 removals, 2 operations, and so on until the end. Now that we filled the first row and the first column, we can fill the other ones by applying the relation. But it depends on if characters match. Remember the recursive solution. So if word1 of I-1 is equal to word2 of G-1, we just move forward in both of them without adding 1. We just take the value of dp of I-1, G-1, like for this cell. And by the way, here I wrote I-1 and G-1 because there is a shift of 1 index in the table. For example, the index 1 in the table represents the index 0 in the word. Then else if they are not equal, we take 1 plus the minimum between the top cell, the left cell, and the top left cell. Because the top cell represents when we remove, and the left cell represents when we insert, and the top left cell represents when we replace. For example, for this cell, we take the minimum between 2, 0, and 1, so it's 0, and we add 1, we get 1. After filling the whole matrix with this method, the minimum of operations required is in the bottom right cell, we return it. For the code of this solution, we first define the function, then we store length of word1 and word2 in n and m respectively. After it, we create a matrix of n+1 rows and n+1 columns. Then, we fill the first row by the index of each cell. Remember that we had 0, 1, 2, 3, etc. And the same thing for the first column. We had 0, 1, 2, 3, etc. Now we can start filling the remaining cells. For that, we use nested for loops, one for rows and one for columns. And inside, if word1 of I-1 matches word2 of G-1, we set that dp of ig takes the value of dp of I-1, G-1. Else, dp of ig becomes 1 plus the minimum between dp of I-1, G, the top cell, dp of I, G-1, the left cell, and dp of I-1, G-1, the top left cell. After filling the matrix, we just return the bottom right cell, which is dp of n, m. For the time complexity, we are just filling the matrix, so we have a time complexity of O of n times m. And for the space complexity, we are using a matrix of n+1 rows and n+1 columns, so the space complexity is O of n times m. But we can optimize it if we want by using only 2 rows or 2 columns as we did in longest common subsequence problem. I hope that you understood the solution to this problem. Check the code below and see you in the next